Alright, hello, my name is Brandon Porath, and today I'll be talking about optimization. So, the definition of optimization is that it's the process of finding the maximum or minimum value of a function with some constraints to it. So, here is an example of what we'll be doing. So, engineers are designing a box-shaped aquarium with a square bottom and an open top. The aquarium must hold 864 feet cubed of water. What dimensions should they use to create an acceptable aquarium with the least amount of glass? Okay, so first you always want to do is draw a picture. So we'll draw a box. It's a horrible box, but it'll work. And to show that it's open, I just shade that and show it's open. So it's a square bottom. So you know that the bottom sides are the same, but you don't know if this side's the same, so we'll make that Y. And the volume is 864 feet cubed, so you can put that up there. And now it's asking what dimension do they use to create an acceptable aquarium with the least amount of glass. So that's surface area. So volume equals length times width times height, and surface area equals x squared, because it's not 2x squared because this side's open, so it's x squared plus each side of this, which is 4 times xy, x times y, and then 4 sides. So length and width are x, so that's volume equals x squared, and h is y. So that's your secondary equation, that's your primary equation. And you're given the volume. So you can do 864 equals x squared y, and just solve for y right here, which is 864 over x squared. And with this, you plug it into this equation. Surface area equals x squared plus 4x times 864 over x squared. So after this, I'm going to just distribute that 4x. So you do SA equals x squared plus 4 times 864. 4 times 864. And that's 3,456 x over x squared. Now I know this looks big, but it comes out smaller in the end. So this x cancels out, and that becomes 1. So surface area equals x squared plus 3,456 over x. And now you take the derivative of that. So surface area equals 2x and minus 3,456 over x squared. Just in case y'all don't know, the derivative of 1 over x equals negative 1 over x squared. So then with this, you set this equal to 0, which is 2x minus 3,456 over x squared. Like that. And you move that over, 3,456 over x squared equals 2x. Multiply that, 3,456 equals 2x cubed. Divide that by 2. And that becomes 1728 equals x cubed. So you take the cube root of that, which equals x, and x comes out to equal 12, and that is feet. So x is 12 feet. So now you have x. That's your critical point. You want to test it first just to make sure that it's a minimum and not a maximum. So you draw your timeline, make that 12, and do your test point. So for here, I'll just do 1 because that's easy. So you plug 1 into your first derivative equation, which is up here, and that comes out to be 2 times 1 minus 3,456 over 1 squared. Which, if you do that in your head, it's going to come out to be negative. So this side's negative down here. And now I do a one above 12. An easy one's just 100. So up here do 2 times 100 minus 3, 4, 5, 6 over 100 squared. And that comes out to be positive. So that's positive. So here goes down and then up. So you know it's a minimum. So now that you know that's a minimum, that's what you want, you know that's your x. So now to solve for y, you plug this back into this one, and you go y equals 864 over 12 squared. So y equals 864 over 144, and y equals 864 divided by 144, and that equals 6, which is a good number. So now you have y equals 6 feet and your x equals 12 feet. And now back to the equation, back to the question, make sure you have all that it requires. It says what dimensions should they use to create an acceptable aquarium with the least amount of glass? So looks like you're done right here. That's what it just asked for y and x. But if the question asked for surface area, it wouldn't be that hard. All you would have to do is plug in x and y into this equation and just solve for the surface area, and that would give you the minimum surface area. For example, if this was like a cost problem, and like the glass on the side costs different than the cost of the glass on the bottom, then that would be easy to do that. So yeah, that's an example of optimization right there. And this can work for many problems, for example, like trying to find the least amount of fencing to enclose an area, and trying to find the maximum amount of glass if this question asks that. So yeah, thank you.